Hello, this is assignment solid mechanics. Okay, I'm Claren Veron from BMka section 1/2. Okay, then this is my fellow teammates Muhammad Amri Sabri bin Ibrahim, Muhammad Hari Ekal bin Muhammad Yusuf, and then Lufti Hadi bin Muhammad Fazan. Okay, this is our assignment about force and factor of safety analysis from actual structure. Okay, this is our introduction. Okay, you can see our model is figure of crane frame structure. Okay, for the figure 2, we already analyzed model from crane frame truss system. This is all from my part. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Lutfi Hadin bin Muhammad Fauzan, and I will be presenting for chapter 2, literature review. Literature review. Mobile crane are complex machine designed for heavy lifting operation. Based on previous research, their structural and operational aspect can be broken down into several key components and functions. According to Zhang et al. 2021, the main structural parts include the telescopic boom, hydraulic cylinders, slewing system, outriggers, and the mobile base. These components must work in coordination to handle both static and dynamic loads during lifting operation. The boom, functioning as a cantilever beam, is particularly critical as it withstands significant bending and compressive force and during operation. Lin and Song 2020 highlight the use of engineering tools such as finite element analysis to simulate stress distribution and optimize crane design. This simulation help engineers reinforce weak point and prevent structural failures under heavy load. Additionally, hydraulic system play a vital role in controlling boom movement and rotation, ensuring smooth and precise operation. Stability is another crucial factor, achieved through outrigger that distribute the crane's weight and prevent tipping. Proper deployment of outrigger is essential, especially when working on uneven or soft ground. In summary, past studies emphasize that mobile crane design must prioritize structural strength, dynamic stability, and operational safety, whether stationary or moving, to ensure reliable and efficient performance in various working conditions. Thank you.
Chapter 3, Methodology. This is the free body diagram for point A, point B, point C and D. Calculation for point C, and this is the equation for point C. The calculation for FBC, we get 1639.57 Newton. The condition of thrust is in tension. B, this is the free body diagram and this is the calculation. For FAB, we get 414.91 Newton. The condition of thrust is in tension. Force AB and force BD. For force AB, we get 1419.90 Newton. The condition of thrust is in tension, and for force BD, we get negative 819.98 Newton. The condition of thrust is in compression.
Assalamualaikum. My name is Muhammad Amir Shamril and I will be presenting Chapter 4 discussion and Chapter 5 conclusion. For our Chapter 4, we look at the different forces acting on a mobile crane during use. First are the external forces. The weight of the lifted loads put the boom in compression and causes bending at the base, especially when the boom is extended. Wind also adds sideway pressure, which can affect balance and create torsion. Then we have braking forces, which happen when the crane moves or stops suddenly. These cause extra stress on the boom and chassis. That's why outriggers are used to spread the load and keep the crane stable. Internally, the crane handles axial loads, bending at joints, and torsional stress when rotating. The hydraulic cylinders also face high pressure when lifting. The boom is made from strong steel like S690QL, which can handle stress without bending. But high stress usually builds up at the base, welds, and near hydraulic parts. Finally, the factor of safety is around 2.0 to 3.0, giving a safe margin for things like wind or repeated use. So overall, the crane design needs to handle both everyday loads and long-term wear. Last but not least is Chapter 5, which is conclusion. From the force analysis, we found that the mobile crane handles both tensile and compressive forces during operation. Members FAB and FBC are in tension with forces of 1419.90 Newton and 1639.57 Newton. Meanwhile, FBD and FCD are in compression with forces of 819.78 Newton and 1828.70 Newton. These values show the crane can safely carry its load and the force distribution is stable. This supports the finding of Lin and Song, who highlighted the role of structure and material strength in crane design. To improve safety, we suggest reinforcing high-stress points and adjusting the boom's shape to reduce strain. Overall, the crane works well under load and stays within safe limits. Thank you.